All right, very good. So today I'm going to talk, this is sort of going to be the most abstract of the lectures. So I'm going to now talk about pure Chern-Simons theory. So yesterday we talked about how, I guess I shouldn't talk when I'm facing the blackboard because there's an echo. But anyway, yesterday we talked about how we could take the fermionic Chern-Simons theory of Lopez and Fradkin, which was obtained by attaching statistical flux quanta to electrons, and integrate out the fermions, provided the composite fermions or the Chern-Simons fermions were in a gapped state, which was some p for lambda levels. If the fermions are gapped, you integrate them out, and then the effective theory that remains is a Chern-Simons theory. Okay? And today we're going to start from that Chern-Simons theory, but from a very abstract point of view, we are going to just start from Chern-Simons theory. We're going to forget about everything else and just look at Chern-Simons theory. What are the constraints on Chern-Simons theory? What can you get out of Chern-Simons theory? Turns out you can get quite a lot. You can get, of course, the Hall conductance as we got yesterday, but you can also get things like the statistics, the fractional charge of the quasiparticles, the statistics of the quasiparticles, and the edge theory as well. So you can get all of those things just starting from the Chern-Simons theory. Okay, so here's the plan of this lecture. So first I'm going to give you some basic introduction to the Dirac monopole, because it turns out that this guy is very crucial in quantizing the level of the Chern-Simons theory. In order to show that the coefficient of the Chern-Simons action is actually quantized, you have to know about the Dirac monopole. Then we're going to talk about Chern-Simons theory as such and the quantization of the level. Okay, this level is something you will understand in a minute. Okay, and we'll also talk about gauge invariance. And this is a little bit non-trivial in Chern-Simons theory, as we will see. There are two kinds of gauge transformations you can make. There are small gauge transformations, there are large gauge transformations, and it's in fact the large gauge transformations that give you the constraint on the level of the Chern-Simons theory. Then we're going to talk about the simplest kind of Chern-Simons theory, and that will pertain to the Laughlin fractions. I'm just going to call it Laughlin Chern-Simons theory. And in this, we will see that you can reproduce sigma xy e squared over k times h. This level will be typically denoted as k. All right. H. Very good. Okay. And we will also get the quasi-particle charge. E over k plus minus, and you also get the statistics. And this is I over k. This is the exchange statistics. Okay. So we'll get all of that from Chern-Simons theory. And then I will give you some physics of the edge of these Laughlin states. Okay, so this will be a pure physics argument. It turns out you can get almost everything from this physics argument. Okay, so everything that I'm saying today can be found in a review by Xiaogang Wen from 1995. I think it's in International Journal of Modern Physics or some such thing. Annals of Physics or International Journal of Modern Physics or one of those, you know, not a physical review journal. Advances in Physics, thank you. It's not a physical review journal. Advances in Physics. Okay. It's a beautiful article. You can spend a whole year looking at that article and learning everything there is in it. And it's great. So I really strongly suggest any of you who's really interested in this field to go and read that article. It contains a lot of stuff. There's also a lot more stuff that I'm going to say today that is in my notes. So there's a bunch of stuff in my notes, obviously much less than what is there in Xiaogang's article, but still it's much more than I will be able to say during this lecture. Okay, so all right, so let's begin. So what is a monopole? a monopole is something that I have mentioned before. Edward also mentioned yesterday. And this is something where the magnetic field goes like some G over R squared ER. Okay, so it points radially outward and it has some strength of G. Okay, very good. Now Dirac had some argument for why it was quantized, and he had this notion of the Dirac string and so on. That's not how we think about it today. Okay, we think about it in a slightly different way. And I'm going to show you the modern way of thinking about these monopoles. So if I try to find the vector potential that corresponds to this monopole, I will find that I can write it in two different ways. One possibility, each of these is proportional to E phi, okay? And it looks like G over 4 pi R. And one possibility is 1 minus cosine theta over sine theta. That's one possibility. Another way, of course, there are an infinite number of possibilities. So let's call them A1 and A2, because as you know, I can make arbitrary gauge transformations, right? These are two different gauges that I'm telling you about. And one of them looks like E phi G over 4 pi R times minus 1 plus cos theta over sine theta. Okay, both of these gauges over almost the entire space, they give you the correct answer. This guy fails at the South Pole, because at the South Pole, this 1 minus cos theta becomes 2, theta is pi, and sine theta vanishes. So this guy fails, but this guy succeeds there, okay? And they give the same curl. This guy fails at the North Pole. But that's okay. So this failure was what led Dirac to think of it as a string. So he thought of it as the end point of some very long solenoid, which is okay. It's not the wrong way to think about it, but it's needlessly complicated. So today we think that the sphere, if you think of it as a sphere, on the sphere we have two patches. On the pole on the patch that contains the North Pole, you use the first form of the vector potential. On the patch that contains the South Pole, you use the second form. They both correspond to the same field. Okay? So there's no problem. Both of these describe the same field. And now I look at a sphere and I know that there is some, if I take my electron in some loop at a constant radius around this monopole, I know that the Aharonov-Bohm phase, so the AB phase accumulated is going to be e to the power I e over h bar times the integral of A dot dl. And this, of course, is a gauge invariant quantity. Okay, it's the integral of A around a loop. Okay, but that is simply, okay, now I have the top here. This is the top of the sphere that is enclosed by the loop, and this guy here is the bottom. Now this, of course, is e to the I e over h bar, the flux that goes through the top, okay, enclosed by the loop. At the same time, when I complete this, so how do I get this? I use Stokes' theorem. I fill in the loop, I make it a surface, and on each, I break up the surface into little loops, and each little loop, it gives me the curl of A, that is B, and that is what gives me this, right? But I could have completed the loop using the bottom of the sphere, right? Now the electron is going around this thing, it only knows this. It doesn't know what I'm using to compute the Stokes theorem, right? It doesn't know whether I've used the top of the loop, the top surface, or the bottom surface. So both answers must be the same. If I use the bottom surface, then of course it'll be e to the minus I e over h bar phi bottom. Why is it minus? Because the sense of the loop is of course different for the bottom, right? The handedness of the loop is important. So I have to use the right hand rule, and therefore there's a minus sign there. So that tells me that if I take e to the I e over h bar phi top plus phi bottom, that is the total flux that is coming out of the sphere. That must be equal to 1. Okay? Now pause for a moment and appreciate this, okay? This is profound. Okay, you see how cool this is? How many of you see how cool it is? Nobody. Then you should keep staring at it until you realize that it's cool. Yeah, use the microphone. What was the question?
Is one that subscript of phi I can't see from here.
Subscript of phi?
Phi.
This one?
Yeah.
This is total flux.
Oh, total flux.
So if I bring everything to one side, you understand this argument, right? The electron accumulates a phase. Okay? That phase has to be the same whether I complete the loop by using Stokes' theorem on the top of the sphere or the bottom of the sphere. Okay, so these two have to be the same. So if I bring this to the other side, phi top plus phi bottom is the total flux of this monopole. Okay? All right, that has to be 1. So what does that mean? What is the total flux of the monopole? It's simply 4 pi g. Right? Think about this. I integrate the magnetic field on the sphere, the surface of the sphere, right? The area of the sphere is 4 pi r squared. The strength of the monopole is g, so it's simply 4 pi g. So this tells me that E over h bar times 4 pi g is 2 pi times some integer. Okay, and therefore the strength of this monopole has to be quantized. It can only be n h bar over 2e. When n is equal to 1, it's called the fundamental monopole. That is the smallest monopole that can exist. Okay? From the looks on your faces, I suspect that you have not seen this argument before. How many of you have seen this before? A few of you. Okay, good. Okay, do you understand this argument? It's very simple, but it's very profound. Questions? All right.
Okay, I have a question. The fact that we used different gauges on the different patches does not affect this argument at all, right?
No, of course not. Because the two gauges, I didn't show you that, but the two gauges differ by a gauge transformation. Okay. So therefore, it cannot affect it, right?
Okay. Yeah.
Because the gauge transformation cannot affect the flux going through a loop. Right? Okay. Mm-hmm. Yeah. Yeah. Yes. The other monopole is at the other end of the universe. So you don't care about it. This is how Dirac thought about it. He thought about a very long solenoid, which was somehow undetectable. But that is not how we think about it today. We think that the fact that you have to use two different gauges is not a problem. It's actually a feature of this thing. Correct. Otherwise, you need to think of the singularity as an actual solenoid. But there is no singularity. It's just a monopole. Okay, so there is no singularity. So this is the modern way of thinking about it. The two patches on the sphere, and then the gauge potential is different. It's related. The two vector potentials are related to each other by a gauge transformation, but they describe the same field. Can you use the microphone so you're recorded? Is it on? Yeah.
Yeah. So the field being quantized is expected here, or
Is what?
expected here, like the result?
Well, it is surprising when you look at it, right? But so Dirac had some other way of doing it. Okay, he used some angular momentum and so on and so forth. Of course, everything has to be consistent in the end. So his argument was correct. Okay, so if you think about the monopole as one end of a very long solenoid, and if you make the solenoid undetectable, I showed you that the other day. what is a solenoid that's undetectable? It has to carry a flux quantum. And that is in fact related very closely to this quantization here. Okay, so there are different ways of thinking about it. To my mind, this is the simplest. This shows you that any monopoles that exist in the universe must be a multiple of the fundamental monopole charge. Okay, it's a surprising result. In fact, Dirac turned the problem around, turned the whole thing around, and he said if there's even a single monopole in the universe, all the charges must be quantized in units of E. Because it was a little surprising at that time to think that, the charges only appear in multiples of E. Why can't you have, I don't know, E times pi as a charge, right? So why can't you have that? But somehow it was never observed. So Dirac said, maybe the reason it's not observed is because somewhere in the universe there's a monopole, and to make everything consistent, all the charges have to be quantized. Yeah. Yes. Yes. So, okay. So that is the argument. Okay. So that is the quantization of the monopole. So what we are going to do as part of this quantization of the level of the Chern-Simons theory, we are going to introduce one of these fundamental monopoles here. Okay. In a way that I will explain in a second. Okay. So, all right. Now we come to Chern-Simons theory. So I'm going to go use imaginary time. So there is some d a mu, and I'm going to write it in its fully relativistically invariant form, and it will look like this. So it will look like e to the, let's say, minus s over h bar, and this s will in fact be some I times some constant c, which I'm going to determine for you now by using these level quantization arguments. And then you have this d tau, d2r, and then you have a mu, epsilon mu nu lambda, d nu a lambda. Okay, that is my action. Now the tau, because I'm in imaginary time, I'm computing some partition function that is naturally a periodic boundary condition in the time direction. Okay, because that's what you're supposed to do when you compute the trace. So the trace of e to the minus beta h, when you compute it in this path integral way in the imaginary time, it actually gives you periodic boundary conditions. So that is what it means to compute the trace. This is an intrinsic part of computation of the partition function where the time direction is periodic. I haven't said anything about the space. So far, I haven't said anything about the space. Okay. Now, later on, I'm going to take the space to be various things. Sometimes I will consider it to be a sphere. Sometimes I will consider it to be a torus. I will always want it to be finite because then you see it helps to control things. Okay, I can count, states if I want to count states and so on, if everything is finite. If things are infinite, then it's hard to count stuff, okay, because things become infinite. Okay, this is what I will use. In my notes, I also use this because there is a part in the notes that I'm not going to cover at all, which is the quantization of pure Chern-Simons theory, which tells you how many degenerate states there are. Okay, so for example, the Laughlin state on a torus has a degeneracy of 3, and that emerges out of Chern-Simons theory. Okay, so all that I'm not covering, but it's in my notes. So we'll use this. Okay, so now let's talk about the gauge invariance of this. So when you talk about Maxwell action, it's obviously gauge invariant because you see what is the gauge transformation. So let's talk about gauge invariance now. So gauge invariance says I should let A go to A mu plus D mu chi with the understanding that this chi is something smooth. I mean, the chi doesn't contain singularities of its own. Okay? So you have this, and now if I had a Maxwell action, so F mu nu, right, which was simply D mu A nu minus D nu A mu, this guy is obviously gauge invariant because chi is smooth, right? So this chi, this part of it is definitely gauge invariant because it already is an anti-symmetric derivative. But that part is hanging out there. So you can ask yourself whether this thing really is gauge invariant. Okay? So this is still only the small gauge transformations I'm thinking about. Okay, where this chi I will specify for you is smooth and periodic. if I have that, then of course, the change in the action, you realize that this part is already gauge invariant. That part, maybe, we'll see, okay? It looks like IC 0 to beta, d tau, d2r, right? And then you have this d mu high times epsilon mu nu lambda, d nu a lambda. Okay, good. Now I claim what I can do is I can take these brackets and shift them like this. Okay, why is that? Because this guy, I'm going to assume f nu lambda is smooth. So the reason I'm not saying that A itself is smooth is because we just saw an example out there on the left board where A is not smooth. A can have singularities. But f nu lambda did not have any singularities, right, on that sphere. So that's why I'm talking about f nu lambda. It's smooth. And now this d mu d nu is an antisymmetric derivative. So this is automatically 0, right? These are the two homogeneous Maxwell's equations, if you want, in this theory. Yeah.
Ganpathy, F has a singularity, right? Because F is something of a curl. So
F does not have a singularity on the sphere.
okay, on the surface of the sphere,
In
it
this
does.
case, in 3 dimensions,
Yeah.
F, of course, B has a singularity here.
Yeah.
But that's a singularity you know. It's like a point charge. Right?
Okay.
Electric field has a singularity. It's a source of point charge.
Yeah, I mean, not on the surface of the sphere, there is no singularity.
That's right. And I'm going to take this, my two-dimensional space to be the surface of a sphere. That's this. Okay? Good? All right. So this term is in fact gauge invariant because it's a total derivative and everything is periodic and smooth. So therefore, this vanishes. Yeah, I can integrate this by powers. The boundary terms cancel because everything is periodic. Great. Right. Okay. So now I have another type of gauge transformation, which are called large gauge transformations. To understand that, let's ask what are the observables of this theory? Okay, so A obviously is not an observable, right? Because it's not gauge invariant. So the most fundamental type of observable I can have, obviously at a point, is simply f nu lambda, right? I could observe that maybe. I want to think about a different kind of observable, somewhat more general, which in some special case can reduce to f nu lambda. Those guys are called Wilson loops. Okay, so they basically involve e to the I e over h bar, the integral of a dot dl, and now I'm using this three-dimensional notation. Okay, so sometimes I will use the vector to be the spatial part of this emergent gauge field. Sometimes I will use it to be the full thing. Okay, so at the moment I'm using this A as a vector in the three-dimensional sense. So it contains A0, A1, and A2. Okay, so in the same way that in that case it was e to the I A dot dl was gauge invariant, this guy is also gauge invariant. Yeah. You don't need any metric because this is a topological theory. You can change the metric and it remains the same. Okay, so you don't need any metric. But if you want, you can impose the usual metric on S1, which is the time direction, and S2, which is space. You don't have to. Okay. Other questions?
Yeah, I have a question regarding the last line that you have written, the delta S. So why this term vanishes? Does it
Why is this term vanishes? You can think about it in the following way. It's d nu, but it's an antisymmetric derivative. So it's like dx dy acting on something minus dy dx acting on something.
Yeah, but that is the extra term that vanishes by that argument, right? Because if you move the delta mu, I mean, out of the chi to the whole.
Yeah.
So the delta, the extra term that comes in, that is the del.
Yeah, the extra term that comes in is epsilon mu nu lambda.
Yeah.
D mu d nu
Yeah.
A lambda.
Yeah. So this vanishes because of the antisymmetry property of the epsilons, right? But the whole thing, the total derivative.
Yeah, the total derivative, I can always integrate by parts. It's total derivative, right?
Yeah.
The total derivative, I can always make it a boundary term.
Okay.
This term, my geometry has no boundary and everything is periodic.
Okay. So it maps into the
Boundary
same
terms
point.
cancel. Think about a Brillouin zone.
Okay.
Everything is periodic on the Brillouin zone.
Yeah.
I take the integral of a derivative and this face of the Brillouin zone will cancel that face.
Oh, okay. Okay.
In a periodic geometry, there are no boundary terms.
Oh, understood.
It's simply zero. Okay. Other questions? Okay. So these are these Wilson loops. In particular, I'm going to take a Wilson loop that looks like this. So let me call it W of R. This is now two-dimensional space now. Okay, and it will look like e to the I e over h bar, the integral 0 to beta of a0 d tau. This is a special Wilson loop. Okay, but it's a large loop. Okay, this is a loop that cannot be shrunk to 0 because it's going from 0 to beta. Okay, this three-dimensional space, there are loops that can be shrunk to 0, loops that cannot. This is a loop that cannot be shrunk. Okay. Now here, I can make the following large gauge.
Sorry, why not?
Sorry, what was the question?
Why can this not be shrunk down to 0?
Why can this not be shrunk down to 0? So let's imagine that two-dimensional space is, I've reduced it to one dimension. So this guy, this time dimension looks like a loop, right? And the space looks like just X, let us say, okay? So now this is your space. So I've reduced space by one dimension. And now I'm taking a loop that goes around like that. So how do I shrink this down to 0? I can't. On the other hand, if I had a loop that was sitting on the surface of this tube, I could shrink it down to 0. So this is a non-contractible loop. Does that answer the question?
Yes. So this relies on the fact that you have a period, the space is periodic, or?
Yeah, because remember, I'm doing path integrals in imaginary time. It's the representation of a partition function. 0 to beta. Beta is inverse temperature.
Okay.
Okay.
Thank you.
Now I have a large gauge transformation, which is the following. It's very simple. I take A naught goes to A naught plus 2n high divided by beta h bar over E. Supposing I do this, I just increase A naught by some constant. Okay. So what happens then? Obviously, this thing, when I integrate this constant from 0 to beta, this beta goes away. When I multiply it by E over h bar, this h bar over E goes away. So I get e to the I 2n pi, so the Wilson loop remains unchanged. Okay. So therefore, this is also a gauge transformation because it does not alter my observables. Okay, but it's a large gauge transformation. So now I'm going to ask myself, in this action over here, where is the action? This is the action right here. If I make a large gauge transformation, does it remain gauge invariant? It's a very delicate thing now. The action itself will not remain gauge invariant. I'll have to ask myself the question. I will demand that under a large gauge transformation, e to the I s over h bar remains invariant. So that is what appears inside the path integral. Okay. So let's do that. All right. So if I rewrite this thing, the only A that I'm going to make the large gauge transformation on is actually A naught. So if I reshuffle this, it will actually look like this. So S really looks like 2IC, one part of S, the part that will matter, will look like this. So you have 0 to beta, d tau, and then there'll be a d2r, of course, and then there'll be A naught, and then d1A2 minus d2A1, which I will conveniently write as F12. There's some other parts of this, but they contain spatial derivatives of A naught. But the spatial derivatives of A naught don't respond to this large gauge transformation because this is a constant. Okay, so I'm ignoring those things now. And now I look at this, and now I'm going to introduce this monopole. So now I'm going to say that my S2, which is space, contains a fundamental monopole. Which is G equals E over 2H bar. Okay. So when I make the gauge transformation, what happens to delta S? So delta S is 2IC. I integrate the change of A naught over beta. So that gives me a 2N pi H bar over E. The beta is gone, right? And now I have a fundamental monopole sitting here. The integral over space of that fundamental monopole gives me just 4 pi times the charge of that monopole, 4 pi G. 4 pi E over 2 H bar. You guys with me? Okay. So this is so let's cancel all the things that can be canceled. And then this will be, what is it? This will be I, C, sorry. No. There. Okay. Good. Okay. So what is it? It is, let me say 2 pi times 2n pi times 4 pi H bar squared over E squared. Okay, so that is delta S. In fact, S itself is not invariant. But what I really want is e to the I S over H bar should be invariant. So in order for e to the I S over H bar, now can I write on this side, or am I not supposed to write on this side? Where's the limit? I'll arbitrarily assume the cutoff to be here. Okay. I just moved the cutoff a little bit, do some RG. Okay. So I want this number, I want e to the I S over H bar to be delta S over H bar to be 1, because then the entire partition function will be invariant. Okay. So this tells me then that I C 2 pi n 4 pi H bar squared over E squared divided by H bar, right? That is delta S over H bar should be I 2 pi times some integer. And that tells you that this C, this constant that was in front of this Chern-Simons action, has to be quantized. I'm going to call it some K, so 4 pi E squared over H bar. And this is the quantization of the level of a Chern-Simons theory. Okay, so for it to be gauge invariant under both small and large gauge transformations, it has to be quantized. Okay, so there's something very fundamental about Chern-Simons theory. Yes, Nirmal.
So my question is, why did you impose the gauge invariance in the partition function level, not in the action level? Because
what is physically observable is the partition function.
Okay.
Or in fact, any correlations. Any correlations of physical observables. That's what is physically observable, right?
Right.
Now the physical observable is already gauge invariant. That's how I've designed my large gauge transformation, right?
Right.
Making sure that it doesn't affect the physical observable. That's what a gauge transformation is, right? It doesn't affect the physical observables.
That's right.
B in the usual electrodynamics.
Right.
Here, the Wilson loops are also not affected.
Mm-hmm.
Okay, that's what a gauge transformation is.
Yeah.
Here, there is a large one, not just the small ones that you can make in.
Right. Right.
Okay, and similarly, I can't observe the action by itself. I can observe correlation function. Correlation functions are, some operator, e to the I s over h bar averaged over everything. So e to the I s over h bar has to be invariant, not s itself.
To start off with, why do you take Wilson loops to be observables?
Because they are, right?
I don't understand why.
Because they're gauge invariant. Just look at this object. Consider this to be some three-dimensional A in this case. It's obviously gauge invariant, right?
Not finite. These are finite gauge transformations, not infinite. So infinitesimal gauge transformations.
Any gauge transformation, finite, infinitesimal, whatever you want. It's invariant.
Okay.
Yeah. So they are gauge invariant. I mean, normally you're thinking of F mu nu, but that's like a local observable. But there are non-local gauge invariant observables, which are these Wilson loops. Okay. Yeah. K is an integer. N is another integer. Then I could have put some monopole, which is not the fundamental monopole. I could have put some other integer. But regardless of any of that, it has to be 2 pi times an integer. What's that?
2 pi n, the left hand side, I see 2 pi n by h star. There n is also an integer, right?
Yeah.
So if you calculate c, that would be some integer by n.
No, I'm saying what can C be? In order to make the right hand side an integer, C has to be an integer, right? Because I can choose any n I want for my large gauge transformation. I could choose n equals 1. I could choose n equals 117. But the same value of C should make the right hand side an integer. What kind of C will do that? It only has to be this, where K is an integer. Now, I don't mean that Z is an operator. I mean, Z is the field of. No. No. No, absolutely not. Yeah. Yeah, yeah. That's not true at all. Yeah. That's the whole point. That was the whole point of this argument. So the modern way of understanding monopoles is not that they are one end of a dipole. No, they just exist. They're particles. They exist. They're not attached to any strings. You can not define the vector potential, but it doesn't mean anything.
Right. If you want to define globally, then they take actually the solenoid. No, that's then put one of the other way to do is you define.
Yeah.
And then you define that there is the transition part.
Right.
Then you don't need
You don't need any strings. Okay. Yeah, yeah. It's got, yeah, there's no physics in the singularity.
Yeah, I have a question.
Yeah.
You chose a large gauge transformation which is constant in time.
Yeah.
So if I choose some other gauge transformation which is not constant, am I going to get some extra information?
Yeah, so the point is, no, you won't, because the thing is that here, I mean, if I quantize it on a torus, see on the sphere, every spatial loop is contractible. But if I took the torus as my space, then I would have some non-contractible loops along the spatial direction as well. And they will give you some information. Then there'll be large gauge transformations along space. And that actually plays an important role in the quantization of the Chern-Simons theory and the degeneracy of the space. Okay, but here, when I'm talking about the sphere being my space, nothing. Okay? All right, so we've quantized the Chern-Simons theory, so we know that it's.
Hello.
Yeah.
So what kind of observables does this Wilson loop correspond to?
Where are you? Yes.
Yeah.
What kind of observables that what?
Wilson loops correspond to
Some non-local observable. In fact, when you think about the confinement or deconfinement of pure gauge theory, these are the observables that you want to study. Okay, you want to study Wilson loops, and you want to study them as they become very large. And you want to know if the energy of these Wilson loops or the average of these Wilson loops is proportional to the e to the area of the Wilson loop or e to the length of the Wilson loop. That is the difference between the confining phase and the deconfined phase.
study them in some scattering experiments in real world.
Which real world are you talking about?
Like in particle physics experiments.
That's not real enough for me.
Okay.
I want it to be more real.
Let me comment on something.
Should you? Let's not go too far afield,
I
Eduardo.
don't want to
Okay,
go
keep it
far.
short.
I want to. Hello?
It has to be switched on. Because I don't want to go off into
Hello?
some tangent about a
No,
philosophical
so the
discussion.
point is that the vector field is gauge dependent. Okay? But you have to look at what are the observables, which are generally gauging values. This is saying that any gauge theory secretly has non-local observables, which are this. And that's the important. So secretly, the content of the theory is actually non-local.
Correct.
Because of this property.
Correct. Correct.
And
F mu nu is a very special local observable. You can think of it as shrinking this loop to 0
Yes.
and then dividing by the area of the loop. That'll give you F mu nu by Stokes' theorem. Okay, so F mu nu is a special case of a Wilson loop. Other questions? Yes. Yeah. Yes, as I told you, I can shrink a Wilson loop and divide by the area and get F mu nu. Right? And I can take many loops and I can take the products of F mu nus. So all observables are given by Wilson loops. Okay. All right, good. So now that we have established, so if there's just one thing you remember from this lecture, just remember this, okay? This is a very beautiful piece of physics. Okay, just remember this. You can forget about everything else about Chern-Simons and blah, 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 but just remember this. So that's why I'm going to erase it first. Okay, so now we have our Chern-Simons theory. We know that K is quantized. And now we're going to write down the simplest possible Chern-Simons theory. Okay, so here we have it. So it's I K over 4 pi E squared over H bar integral d tau d2r and then A dA. So you guys already know about A dA, right? So we introduced that yesterday as a compact way of writing all those epsilons and mu's and nus and lambdas and so on. Okay. Okay, so this theory is there. So what do you do with it? How do you couple it to something that you know? So what we want in the quantum Hall effect is to couple some charges and currents to an external magnetic and perhaps some probe electric fields. So how do you couple that? So you have this A, which is your actual physical vector potential of E and M. And I want to couple this theory to that. So when I couple anything to electromagnetism, I couple it through some current, right? Typically, that's how anything couples to electromagnetism. And the current has to have a very important property that it has to be conserved. Otherwise, the theory will not be consistent with gauge invariance. Okay, so it has to be a conserved current. It has to obey the continuity equation. How can I take this theory and construct from it something that's a conserved current? There's only one option, and that is this. Okay, so it has to be something proportional to this, because this guy is automatically conserved, as we discovered when we did the gauge invariance argument, right? Because it's two cross derivatives, and it's anti-symmetrized, so it's conserved. Okay, so now I claim that the proper normalization of this, as you will see when we come to it, is this. This should be the physical electrical current. Okay. So what I'm going to do now is I'm going to couple it in that way and ask, what is the full theory? So this is SCS plus A. I'm going to write it. So this is, d tau d2r E squared over H bar, and here it comes. So there's an I K over 4 pi ADA, okay, and plus or minus, it doesn't really matter to me. Okay, so let's put a minus here, and then this will be a 1 over 2 pi, let me write it as A, B, little a. There's an I everywhere. Why is there a 2 instead of 4? Very good. So now if I take this action here, and I again demand exactly the same kind of gauge impedance that I demanded. Okay, but now I also make capital A able to have a monopole. So I assume that there's a real electromagnetic monopole somewhere in the universe. Okay, and somehow I'm able to put it inside my sphere or not. Okay, that's up to me. Okay, if I assume that, then this coefficient also gets quantized by exactly the same argument that we ran through. Okay, work it out. It's a very good exercise. Work it out, and you will see that this is 1 over 2 pi because this is a cross term. Okay, that's why it works like that. Okay, good. So now let's ask ourselves, what is the saddle point of this theory? Okay, so all I have to do is find the equation of motion for little a. So when I do that, I find k over 2 pi dA minus 1 over 2 pi dA equals 0. You guys see that? Is it obvious? There's a factor of 2 because this is quadratic in A. Okay. Now this guy I can also write as minus 1 over 2 pi little a d capital A. These two are really the same. Again, you can go and verify it by manipulating all the indices using the antisymmetry of epsilon. You will see that this is true. Okay, so now let's put in all the factors that make it into the real charge operator, the current operator. Okay, so let's put in e squared over 2 pi h bar here. So there'll be an e squared over 2 pi h bar here. Now I want to know what is the charge. Okay, what is the charge density of this guy? That'll be mu equals 0, right? So this says J electron 0, which is the charge density, should be the 0th component of this. The 0th component of that is e squared over 2 pi h bar k times the curl of A, the physical A, the electromagnetic A. That is the magnetic field. Okay, good. But of course, you guys secretly know that EB is equal to h bar over L squared, right? You guys know this, right? Because L is the square root of h bar over EB. Okay, so I put all of that in, and I find that this is E times 1 over K times 2 pi L squared. In other words, this is nu E over 2 pi L squared. So this particular Chern-Simons theory that I've written down for you, coupled in this way to the external electromagnetic field, in fact corresponds to nu equals 1 over K. Okay. Now this theory is agnostic about whether K is even or odd or whatever. K could be any integer, right? But we know from what we have done before that in order for you to describe a fermion, electronic Laughlin state, K has to be odd. Otherwise, you can't write down the Laughlin function, Laughlin wave function, because it wouldn't be antisymmetric. Okay, good. So this is the effective field theory description of the Laughlin states for any K that is odd. Okay, questions?
Extend to Laughlin states, this formalism.
This is the Laughlin state.
No, but this is for any generic K, right?
But when K is odd, it's the electronic Laughlin state. When K is even, it's what's called a bosonic Laughlin state. Those states also exist.
So we observe them also. Like next.
Actually, I don't know whether they've actually been observed, but there are proposals, I believe, for cold atom gases, where you can have bosonic atoms or fermionic atoms, and you can tune the interactions between them. And so there are proposals, I believe, for making bosonic Laughlin states, where the analog of the magnetic field is provided by the rotation of the trap. There's some complicated stuff. Okay? Maybe somebody here knows about this. I don't. Maybe there have been advances. They have to rotate, yeah, but have they actually observed it? They haven't observed it yet. Yeah. Okay. So now, let's go on to describe quasi-particles. Quasi-particles and quasi-holes. To describe them, what I want to do now is I want to couple this emergent vector potential little a to some other current. Okay, this other current is not the electromagnetic current, which I'm representing by capital J. Okay, that is the electromagnetic current. That's the the thing you measure in your ammeter and your you measure your charge density. This guy is some other current. So I'm going to couple it by saying that now I have my S, which is now I E squared over H bar. And then, of course, I have my d tau d2r. And I have K over 4 pi A dA minus 1 over 2 pi A dA. Okay. And then a minus 1 over 2 pi J mu A mu. So this is little j. This is going to be like your quasi-particle current. Okay. So now let me solve the equation without worrying about this for a second. Okay. And you can easily convince yourself why it's justified. So this J mu, for a start, let me say that this is simply, so this is X, which is both R and tau. Let me say that this is simply delta of mu, comma 0, delta 2 of R minus R naught. So I have some J mu, which is like a source. It's a delta function sitting at a fixed location on my sphere, and it's not moving in time. So there's no time dependence of this guy. Okay, and I want to find out what are its properties. So what do? I take this guy and I solve the equation of motion of this little a. Okay. So as usual, what do I find? I find K over 2 pi dA, right? And then let me introduce this as well. Okay, it doesn't matter. Okay, minus 1 over 2 pi dA, right? You already know that from before. Now there's this part here, right? And then there's minus 1 over 2 pi J mu. Now you might be worried that there's a mu here, but there's no mu there. But remember what this stands for. This stands for epsilon mu nu lambda d nu a lambda. Okay, so with that understanding, everything is good. And so you find that this excess, so there's of course already some charge density because it's a 1/3 Laughlin state. I need an equals 0. Let me minimize my effort and say this. Okay. Since I'm minimizing the action, I might as well minimize my own action. Okay.
So you added a charge
Yeah.
at that particular point.
A charge of the emergent gauge field,
Yeah.
not the electromagnetic charge. Yes, that's right. Okay. So what is the excess charge? Now I mean electromagnetic charge. What is the excess electromagnetic charge? Okay. So there is this, so let me call this delta A. So I can see that there is an average of this delta A. So there was something even before I added this J mu, and then there's something more that comes because of that J mu. Okay. There's something more that comes because of the J mu, looks like this. So I have epsilon mu nu lambda d nu a lambda should be equal to 1 over k. So this is the excess I'm talking about, okay? Should be equal to 1 over k times the delta function. 0, and this is only true for mu equals 0, okay? So let me call this F12. Okay? Now, in order to find the electromagnetic charge, I have to multiply F12 by E squared over 2 pi H bar. So let me do that. So let me say J, delta J0 electromagnetic is E squared over 2 pi h bar times this, E squared over 2 pi h bar. Okay. And lo and behold, have I done the correct thing here? Are all the units matching? I need a factor of what? I'm missing some factors of E. I think the J itself, I'm sorry. Where's the J? Yes, I better have a E. I think I need a E over 2 pi here. Okay, that's what I really need. Okay, I need an E over 2 pi, yes. So if I have an E over 2 pi, that's what I need. Okay, so this is, sorry, E. Okay, so that's what has to be true. And no, I messed up somehow. I've messed up. Okay, just give me a second. No, this has to have an E because this is a charge, right? So it has to be one E. There has to be one E. Yeah. But it has to be one E, but it's the 1 over K that I'm trying to get at here. So this should end up coming to be E over K, okay, times this delta function. Okay, so go home and work it out. There's some small algebra mistake here, but you can figure it out.
Can you give some feel what is the meaning of
So you can imagine threading. So let's go back to what Laughlin did. Okay, you can imagine threading a tiny solenoid with a unit of magnetic flux, and that will create one of these quasi-particles.
Why this extra physical flux tube?
Yeah. Very good, because it has the same physical properties. It has the same charge. It has the same statistics. I'm going to talk about statistics now. So you identify those two. So in other words, in the Laughlin state, you had a very physical mechanism for creating a quasi-particle or a quasi-hole.
Well, I couldn't understood if you
Yeah.
took the physical A.
Yeah.
And then added some
Yes.
flux tube, localized flux tube.
Right.
That will do the work.
Right.
But this is not the
I think you
Can
can
I
do
make
that
a
as
comment?
well. Yeah, please go ahead.
So if you go to your lecture,
Yeah.
so there is a covariant derivative that relates you call it I call them the composite fermions. I call them you call them the Chern-Simons fermions.
Yes.
So we'll negotiate the name later.
Yes.
And so that's how they couple. There's a minimal coupling between them.
Right.
So if you now imagine that you look at that the theory has a gap, as he showed yesterday, and you look at the word lines of an excitation that corresponds to an extra one of these Chern-Simons fermions.
That's right.
So that's how it's going to enter. And this is coming from the minimal coupling.
Yeah.
But my question is actually, I understand what you're saying. My question is that I had two options.
Yeah.
One option is to take this source term with the little j. The other to say, I don't understand anything. I just will take an extra physical
Actually,
flux
you can do that
with
too.
with the large A.
You can do that too.
What will be the difference?
There is no difference. You can actually see it right here, okay? Because supposing on this D capital A, supposing I added an extra delta function, you would get exactly this plus that delta function divided by K, right? So you would get the same thing. The only problem is that when I want to manipulate these guys, supposing I want to braid them, then I'll have a very hard time because then I'll have to give coordinates to the delta function and do something. This is a much easier way and it's equivalent. Okay, because these J mu's are something that's under my control. These are some external sources. I can move them around. Okay. Yeah. Right, whereas if I had the A, then I couldn't make them move around, right? In time. That's the problem. Other questions? Okay, so now this is a calculation I'm not going to do, but it's done in my notes in gory detail. Okay, so the charge we've already established, E over K. Now the fractional statistics. What you can do is you can take two of them. Okay, so you can take your J to be delta mu comma 0 times, let us say one of them, there's some 2 pi, of course. Maybe there's an E, maybe there isn't an E. Okay, we'll negotiate that later. And so what you have is delta, let's say, of R minus R1 plus you have a delta of R minus R2 of tau. Okay, so what I'm thinking about now is I have one fixed quasi-particle. I'm going to move another quasi-particle around, okay, in a circle. So when I do it in a complete circle, I can evaluate the entire partition function. How do I do that? Because this here is fully quadratic. Yeah. Because I'm sorry. No, that's not quite right. So this is simply the charge. There's also some current. Okay, so there's some, so let me write it like this. So J0 is like that. Okay, J0 is like that. J1 is like, x2 dot of tau over 2 pi, okay, times this delta 2 of R minus R2 of tau. And J2 is, sorry, no vector, y2 dot of tau over 2 pi. Okay. So there is going to be now a spatial current because one of the quasi-particles is moving. Okay. So you have now a slightly more complicated situation, but regardless, the theory is completely quadratic. So you can integrate out A, and that is completely equivalent to solving the equation of motion for A and plugging it back into the action. You do it, and you find that this gives you a phase of 2 pi by k. So that tells you that the exchange statistics is pi over k because this was a complete circle. Okay, this is really the simplest way of computing the exchange statistics of quasi-particles. This is for a full exchange. So one guy is sitting here, the other guy moves all the way around. No, this is 2 pi. So the exchange statistics is pi. That's exactly what I said. That's exactly what I said. Okay, but for the exchange, it is 2 pi. Sorry, it's pi. Okay.
Can I comment something quickly? This is actually equivalent to the very phase calculation of
Arrowa-Schrieffer-Wilczek. Absolutely. Yeah.
And it's equivalent because you're essentially you send the gap to infinity. So you're always in the adiabatic.
Yes. Yes. Okay. Quasi-particle. But when you say physical, it's a Z0 that they were moving. All right. So those are basically all the topological properties of the Laughlin states have now been recovered. Okay, the bulk Laughlin states are now been recovered in the Chern-Simons. And let's go on to the edge. Okay, so I have 20 minutes remaining. I'm probably not going to get to K-matrix theory, but it's all in my notes. And very quickly, before Eduardo starts talking tomorrow morning, you should read up on K-matrix theory. So, okay. He will also introduce it, but let me see how much time I have. Okay, so what I'm now going to do is go to the edge. Okay, but at first I'm going to go, so there's a way of deriving the edge from Chern-Simons theory itself, but I'm not going to do that because it's, very technical, very mathematical. You'll just watch me doing a lot of gymnastics with, fields and things. So let's not do that. Let's do something very physical, something that you'll actually remember. Okay, so this will be the physics of the edge. So here's what Xiaogang Wen says. You think of a droplet. So we already discussed the droplet. So let's say this is a nu equals 1 over k droplet. Right? There's some maximum value of m that is occupied, and beyond that, it's empty. Now, what I'm going to do is I'm going to distort this droplet a little bit, and I'm going to create some long wavelength excitations on the edge. And that's what this droplet looks like now. I'm going to look at this region over here, and I'm going to describe it in some hydrodynamic approach. Okay, so let's see how that works. So what do I expect? Inside, my electron has negative charge. The magnetic field is pointing down, right? So when an electron goes this way, there's a V cross B is this, but the charge is negative, so it's that. So therefore, the cyclotron orbits are looking like this. They go clockwise. All right. But near the edge, I have some electric fields, right? What are these electric fields? They're pointing out. These are the electric fields. That is what is in fact confining the electrons to sit in this droplet. Okay. When we talked about disorder, we talked about something called guiding center drift. Okay, you remember that, right? So guiding center drift says whenever there's an electric field, when the electron goes along the direction of the electric field, it slows down. When it goes against it, it speeds up. Okay. So what happens is that it does that. So it's doing this. It's slowing down. It's doing that. So the overall direction of motion is this at the edge. Okay, counterclockwise at the edge. All right. So what do you expect of this thing? You expect that if I create a lump and the drift velocity of this is basically E over B. It depends on the electric field at the edge, also on the overall magnetic field going through the sample. So this velocity is the velocity of a lump. So if I just create one lump on the edge, this is what I expect the dynamics to be, right? This lump will move along the edge with that velocity. Right? You guys understand that? This simple physics. Okay? So therefore, what I expect is if I have a delta rho of x, let me call the coordinate along that direction x. Okay, so if I have a delta rho of x, then I basically expect that d by dt of this guy, or del by del t of this guy, should be equal to v del by del x of this guy. Right? This represents a wave that is moving along the edge, because the solution to this equation is simply some function which is a function of x minus vt. Right? So you've all solved the wave equation. The wave equation is normally second order. This is an example of a first order wave equation because these waves only go in one direction. Okay, these are chiral waves. All right? So this is the equation that you expect. And these are the coefficients. You're going to use this equation, this physics equation, to derive some commutation relations, which will be very important in what follows, and perhaps also in what Eduardo is going to tell you about. Okay, so now let's ask ourselves, what is the Hamiltonian? I'm going to take a semi-classical approach. I'm going to compute the classical energy of this system, of this lump here, and then I'm going to quantize it. So what's the classical energy? So what is this? So this little difference here at some point x, let me call it delta r of x. By that, I mean the deviation of the radius of the droplet from its unperturbed radius. Okay. Now I know that this delta rho of x should be delta r of x times rho naught. And what is this rho naught? Delta R of x times nu over 2 pi L squared, 1 over k, 2 pi L squared. There's a fraction 1 over k. Okay, good. Now, what is the energy of this guy? Well, some electrons are here, some electrons are there. So really the energy is the average. Okay, so therefore the energy should be the Hamiltonian, which is the energy should be dx. Okay, so integrate over all this, the surface of this droplet times 1/2 of E delta R delta rho. You guys with me? So some part of this droplet has low energy because it's sitting at the original place. Some part is very high. The average is 1/2 delta R. Okay. So this times that is an energy. E times E is a force. This is an energy. Delta rho is a number per unit length. You can check. This is a length. This is a number per length squared. So this is a number per unit length. So this has units of energy. Okay. Good. All right. So that is correct. But think about the energy, right? The electric field is a constant. As the density of the bulk. Absolutely. Absolutely. Yeah, so you think of it as an incompressible droplet, right? You realize it's incompressible. It doesn't want to change its density. So the cartoon is that the whole droplet just deforms. Question?
The electric field is perpendicular to the direction of motion of electrons. So what is contributing to the energy here?
Well, look, you're climbing up the potential hill when you go this way, right?
No, but the electrons are moving in the clockwise direction.
Electrons will be moving anyway, but where are they located? So when they were here, my normalization is such that when they were on the boundary of the original circular droplet, their energy was 0. So if they go above it, they're climbing up the potential hill. So they gain in energy.
Okay, so there is a radial component to the electrons also, radial velocity.
No, it's not a velocity. There are electrons all over here. They may be moving, but I'm talking about the instantaneous energy.
Is it the local potential with respect to the boundary of that droplet?
Exactly what it is.
Okay.
That's the point.
Okay.
So there's little e times capital E is a force.
Okay.
Force times distance is the work done by the electric field in pushing the electrons there, right? So that's what it is. Question? Because that is why the electrons are sitting inside, right? If the electric field is outside, that means the positive charges are sitting here. Electrons want to be near the positive charge. They don't want to go out. Okay? All good? All right. So this is what you understand the half now? Right? Some electrons are low, close to the boundary. Some electrons are high. The average is half. So there's no negotiating room here, okay? This is it. There's no fudge factors, nothing. All the factors are correct. Okay, so let's work it out. So now I'm going to express this delta rho itself in terms of, delta R in terms of delta rho. I want to write it as a density-density interaction, okay? So let me do that. So what do I get? I get 1/2 little e capital E. When I convert delta R to delta rho, I will get something that looks like a k 2 pi L squared here, right? And then I will get integral dx delta rho of x squared. Okay, 2 pi L squared is basically 2 pi h bar over EB. Let me cancel the e's. Let me take my E over B. Velocity. Okay, velocity is E over B. Okay, so here's my Hamiltonian. V over nu 2 pi h bar integral dx 1/2 delta rho of x squared. Good. Now comes the punchline. So I want this equation of motion. How should I quantize the theory in order to get that equation of motion? This looks impossible because normally you say density commutes with the density. So therefore, there's no possibility of commuting anything because the Hamiltonian commutes with the density. So the density has no time dependence, right? Things that commute to the Hamiltonian have no time dependence. It looks impossible a priori. It's not impossible. Yeah. There is no kinetic term because we are in the lowest Landau level. In the lowest Landau level, all one-body states have the same energy. Okay, everything is either interactions or external electric fields. Okay, good. All right, so how do we quantize this theory so as to get the correct equation of motion? So you guess. So here's what you guess. So let's go to K-space. Let us make X finite. So X belongs to 0, L with periodic boundary conditions. Okay. So that allows me to expand this delta rho of X in some Fourier modes. Okay. Let me expand that, and let's imagine that there's this delta rho is now a function of Q and T. And this Hamiltonian now, of course, this Q will have positive and negative pieces. So this delta rho of X should be, of course, equal to some whatever normalization you want, right? So let me think about some sum over Q, right? Delta rho of Q of T perhaps, right? This is X and T, and so this will be some e to the I QX. I'm going to break it up into positive and negative Q, okay? And so I'm going to rewrite this Hamiltonian. So there'll be two terms. There'll be a rho of Q and a rho of minus Q, right? Because when I integrate over dx, right, I'll get rho of Q, rho of minus Q. And so I will rewrite it in the following way. So I'll get pi h bar over nu V sum only over greater than 0 Q. Okay. Delta rho Q, delta rho minus Q. That'll be my Hamiltonian. Okay, and from this, what do I want? I want to get an equation of motion that looks like the classical one. And that is this one. If I go to K-space on this guy, I will find that delta rho Q dot is equal to V times Q times delta rho of Q. You guys agree with that? Because the Qth component of this, the d by dx will bring down an extra Q. Okay, maybe there's some I there. That's what it should look like. Okay? How can I arrange it so that that is what happens in this theory? And the answer is, there's a unique answer, and that answer is that I want delta rho of Q and delta rho of minus Q to actually have a non-zero commutator. Not only is it non-zero, moreover, it must be nu over 2 pi h bar times Q times delta Q plus Q prime 0. This is a very famous object. It's been encountered before in mathematics and physics. It's called the Kac-Moody algebra. Okay, so you basically guessed the Kac-Moody algebra as the unique way to quantize this theory so that you get the right equation of motion for the lump of density. Question? Because otherwise, if the commutator is 0, you know that the time dependence of anything is governed by the commutator with the Hamiltonian. If it commutes with the Hamiltonian, it has no time dependence. You want it to have a time dependence, right? This is the only option. Okay. Now this Kac-Moody algebra has a very long history. I believe it was first discovered by mathematicians in the, I don't know, in the 1950s or something like that, from ancient times. And then later on, it found application in physics in conformal field theories. It is a very, very important part of conformal field theories as well. Current algebras. Yeah. No, there's kinetic energy. You mean like 1/2 mv squared kind of energy? It's going to be very tiny. You're right. There is going to be something, but it's going to be extremely tiny because this E is very small compared to B. Okay. I think what it may do is contribute to some nonlinearity in the equation of motion, or maybe it renormalizes the velocity slightly or something. It's going to be some very minor effect.
The velocity will not be constant.
Yeah.
It will be a
Function of amplitude or something. There's some nonlinearity. Okay. All right. So this is the Kac-Moody algebra. And now I'm going to tell you some facts. I'm not going to be able to derive the facts, but it is done in my notes. There is an alternative way to come to this theory, which is that you start with the Chern-Simons theory. Previously, we had a space which was S2. It didn't have any boundaries. But now you put it on a disk and you ask yourself, what happens at the boundary? You do something because the gauge transformations, if you allow arbitrary gauge transformations, then the system is not gauge invariant. You got to do something like restricting the gauge transformations to be 0 on the edge. Okay, what does that mean? That means that degrees of freedom, gauge degrees of freedom, which were redundant in the full theory, have now become physical at the edge because they are no longer subject to the gauge redundancy, okay, because those gauge transformations have to vanish at the edge. So some degrees of freedom, which were formerly gauge, like A, have become physical degrees of freedom at the edge. And that physical degree of freedom is represented by a bosonic field phi. So it turns out that this can be recovered from the Chern-Simons action at the edge, okay? And that looks like K over some 4 pi h bar, maybe some E squared, okay, dx d tau, okay, only one x now because you'll come to the edge. And it looks something like this, dx phi d tau phi minus v dx phi. Okay, this is the theory, the action that results from restricting the Chern-Simons theory to the edge. And it turns out there's a one-to-one correspondence between these two guys if you assume that this delta rho of x is actually 1 over 2 pi dx phi. Okay. All right, I have 39 seconds left. And in those 39 seconds, I will tell you that because this guy is descended from secretly from some A, remember this A was allowed to have monopoles. So this A is really a compact gauge field. Okay, this phi, therefore, which is descended from A, is also compact. So it should be periodic modulo 2 pi. So you're allowed to take e to the I n phi as a legitimate operator in the theory, where n is an integer. Okay, because this operator has to be, has to reproduce itself with phi modulo 2 pi. Okay, it turns out that in this theory, e to the I phi is the quasi-particle on the edge. E to the I k phi, naturally, is the electron on the edge. And in fact, you're going to hear some talks later on about how to theoretically calculate various things on the edge. So we heard this beautiful talk by Gwendal Fev yesterday on the anyon collider. And he referred to some calculations. And I believe that Bernd Rosenau is going to give us a theory talk about exactly that experiment and how he does the calculations. In these calculations, these people often use this formalism. Sometimes this formalism is also called bosonization. Okay. And then the K matrices, the K matrix theory of all abelian quantum Hall fluids, I just simply have no time to cover that. So you will have to depend on the notes. It's actually covered in the notes. There are 3 parts to lecture 3. There's part 1, part 2, and part 3. And I believe part 2 is the K matrices, which I didn't even touch upon. Okay, it's just a generalization of this integer K. The K matrix is a matrix of integers. It has certain properties. Okay, questions? Yeah. The mic.
Restricting our gauge to A equals 0. Is that because there is an infinite potential at the boundary?
No, it's not because of that. It doesn't matter what the potential is. The fact is that if you allow unrestricted gauge transformations, the Chern-Simons action itself is not gauge invariant at the edge. Okay. So in order to make it gauge invariant, you have to restrict your gauge transformations such that the gauge transformation vanishes at the edge. Okay. There is another way to think about this. The other way to think about it is the Chern-Simons theory itself is not gauge invariant, but you add an extra edge action, which together with the Chern-Simons theory becomes gauge invariant. Okay, so you add something to it that makes it gauge invariant, and that something is this. So those are the 2 ways of thinking about it. Eduardo has something to say about this.
Even in electromagnetism, there is the same problem.
Speak up.
Even in electromagnetism, there is the same problem. So when you take a battery, you say this is the voltage.
Yeah.
Essentially, what you are looking at is the difference between the gauge potential between the 2 electrons.
Yes.
And that's because, and that's the physical, is the voltage difference. That's the analog of it.
Yeah.
So in any gauge theory, you need to essentially fix the gauge transformations to vanish from the boundary.
Right.
What's left is a physical.
Right.
observable.
Right. I think Yuval had a question. There was another question there. Please find a mic in the meantime. Yeah. Speak up. Is it on? Yeah.
The set of equations that
Yeah.
you wrote,
Yeah.
e to the I phi being quasi-particle and e to the I k phi being the electron,
Yeah.
are a matter of convention, and you must write also the commutators of the phi
Yes.
in order to fix this convention.
Absolutely. Of course.
So, like, you've quantized the theory on the sphere, and you say that you can quantize it on a torus as well.
Yeah.
What if you try to quantize it on some non-compact surface?
So the idea is that if you have a theory that's well defined, it shouldn't matter. I should be able to put it on any manifold, and it should work.
But here, in some sense, we are relying that the space has some finiteness, and we can.
No, the point is that if I'm able to quantize it on any manifold, one of those manifolds is S2. So I should be able to do it. You can ask the question, if I quantize it on other surfaces, will there be extra constraints?
I mean, quantize it on a non-compact surface, like which is like not bounded. So
I know, but what I'm saying is that the theory, as a theory, right, it should be valid. So when I make a quantum Hall state, let's imagine that I can make a quantum Hall state on a torus, I can make a quantum Hall state on a sphere. It's the same quantum Hall state, right? I mean, physically, it's the same state. So it should be describable by the same theory, no matter what surface, what manifold I put it on. So the same theory should work for an arbitrary manifold. Now, if I put it on the plane, I don't get any constraints. But if I put it on the sphere, I do get a constraint that K is an integer. So therefore I say, oh, but then I can go on and put it on many other surfaces. But the fact that K is an integer is enough, it turns out. There are no further constraints. So that theory will work for any surface, any manifold for my quantum Hall system. And so therefore that is the correct theory. Suraj.
So it's on the appearance of the right-hand side of the non-trivial brackets, the Kac-Moody algebra. So if you see, it's quote unquote the way it was introduced for it was for quote unquote quantization, right?
Yeah.
But if you really see, it's coming from the requirement that you need chiral waves on the surface of an incompressible classical fluid.
Mhm.
Because you demanded that Hamiltonian and you required that the Hamiltonian and the, so if I just take Poisson brackets,
Yeah.
one can still obtain that.
Yeah.
So there is not really quantum as such
Right.
as of now.
No, that's all true. But remember, this whole thing, there's H bar right from the beginning, sitting here.
Sure, yeah. But I
So
could have just
the problem is
assumed that this is a
quantum from the beginning.
classical incompressible fluid and I have chiral waves.
Yeah,
And
yeah, yeah. Yeah. Yeah, you can. I mean, you can play various games, but it's all the same thing, right? And Poisson bracket is the same as the commutator, right? Come on, we'll have to have another fight. For me, it's all the same thing. Okay, there's no real difference.
When we quantize the theory on the sphere, we get this k integer. But again, when you this in the S theory, we are still assuming k to be integer.
Right. So let me repeat the answer that I gave to an earlier question. This is an important point. The point is that the bulk of the quantum Hall system doesn't care about what the edge is. Okay. So this theory, this Chern-Simons theory, describes the bulk. It should be able to describe the bulk on an arbitrary manifold. The same theory. I shouldn't have to say if I describe it on a plane, it is this theory. If I describe it on a sphere, it's the another theory, and on a torus, it's the third theory. That doesn't make any sense because physically the state is the same. So whatever theory I have should be able to describe it on an arbitrary manifold. Very important physical point. That is why, even though I used a sphere to derive the quantization of the level K, it's true for any manifold. A very important point. Question? Use the mic.
So if I put this theory on, let's say, some genus G Riemann surface, will there be any signature of the genus in the physics?
Yeah.
Where, what would that be?
Nothing. There will be no extra constraints. The fact that K is an integer, it turns out is enough to quantize it on any arbitrary genus surface.
There would be no extra constraints, I get that, but will there be any signature of the genus in?
Yeah, there'll be different Wilson loops.
Okay.
So around every handle, there'll be a different Wilson loop.
Okay.
And you'll have other large non-contractible loops. So those will be other observables of the theory.
But that does not do anything extra, you're saying?
No, it's not a part of the action, right?
Okay.
The action will be the same, but except the spatial manifold on which you.
But you'll have a lot of new operators coming from, okay.
Exactly. There'll be some other non-contractible Wilson loops. And of course, the genus will change. There'll be some other stuff. There's some other question somewhere.
Is there a way to add interactions to this Chern-Simons theory?
So let's ask, what kind of interactions do you want to add?
So yesterday you added an interaction which was like del cross A dot del cross A.
Right. So the point is, this is, as I said, something called a derivative expansion. So you're looking to describe, this is an effective field theory. You're trying to describe something at low energies and long wavelengths. So you want to keep terms with the minimum number of derivatives, and then you can add other terms with higher and higher derivatives. They will be less and less important in the long wavelength, low energy limit. For example, I don't have any fields other than little a, right? Any dynamical fields. So therefore, I could have added a term f mu nu squared for the little a. I could do that. There's also quadratic in little a, but it has one higher derivative than that term. Therefore, it will be less important at long wavelengths and low energies. So, and it will be non-universal. Its coefficient is not quantized. Okay, so there will be non-universal contributions. And so you can add even further things. You can add maybe something that looks like f mu nu, f nu lambda, f lambda mu. Okay, you could do that. You could add any number of terms, but they're all higher and higher derivative terms. And so they'll be less important, successively less important in the long wavelength limit. And so since what I'm trying to describe is a long wavelength, low energy effective theory, remember, I've already tossed out everything above the gap. There are fermion excitations that I've completely tossed out. Okay, so I'm not trying to describe everything. This is a low energy effective theory.
Okay, you made a comment about the compactness of the boson.
Who is talking?
Online.
Online, yeah.
Yeah. So the compactness of the boson, does it depend at all on the compactness of the manifold it lives on?
Of the what? The line? No, it doesn't. No. The point is that it is a line, okay? That's all that matters. It's on the edge. The compactness of this guy is descended from the compactness of A, right? Remember, we were able to put a monopole of little a, that was little f12. I was able to put that inside the S2. And that itself should tell you that this little a is compact.
Mm-hmm.
And so little a is compact, phi is descended from little a, it is also compact. It has nothing to do with whether I close the line as a circle or not. Even an infinite line will have a compact phi.
Mm-hmm. No, I asked this question because in the literature of quantumologists, there's people usually consider disks, and there's, okay, they talk about compactness of bosons, and then there's always this confusion whether this compactness is related to the compactness of the edge itself or not. So, okay.
No.
All right. Thank you.
You're right in that.
Speak up.
Yeah. What you're saying is correct, but if you actually want to look at it from the point of view of the boson alone, it's related to this expression I had yesterday, that if you want to change the total charge, so suppose you add some charge in the bulk, or you insert a flux.
I don't think you're
suppose you insert a flux in the bulk.
Yeah.
Then there will be some excess charge at the boundary. And that changes the boundary conditions for phi from periodic to there will be an extra twist, an extra term that is related to that extra charge. So this is related to Laughlin's argument that it expels the charge from the location of the solenoid and it ends up at the edge of the theory, of the system.
Yeah.
And that thing will actually, so you're in a different sector of theory. This is not, here you're assuming that you're in the neutral sector because there's so many excess.
Yeah. So phi
charge
goes from 0 to 0 around.
Yes.
But you're saying if
So
you add a charge, phi will go from 0 to 2 pi as I go
Correct.
around.
And that's and how these lamps are related essentially to the amount of charge that is expelled from the center. So this is actually the boundary edge correspondence.
Yeah. But in any real sample, if you put contacts and so on, then there are contacts to suck away any charge that you want. So, yeah. Other questions? Okay, so I will be around and Eduardo will also be around. And so you can bug either of us. If you don't find me, if I run away, you can find Eduardo. And you can bug either of us about anything to do with Chern-Simons theory. Okay? I mean, really, you should bug Eduardo. All right.